sure you know that you need to, these things need to go kind of in lockstep. So, in a sense, the more data you have, you can afford to do the more complex modeling, and the more complex modeling, the more difficult to figure out what's going on, unless you went to some physics-based thing, but like nobody really does that. At the end of the day, we're using these linear regression trees, and what we've done specifically for the alternative I'm going to talk about the off-target, but unless there are questions about the on-target first, that's sort of the much simpler one from a machine learning perspective. It was much, much easier to do. The next one was a bit of a nightmare. Yeah, we can, absolutely, yeah. Yeah. Yeah, definitely. Yep, okay. Right. So this is a much more challenging problem for us for a number of reasons. And so one thing is that we're now kind of looking for accidents, right? We don't have this perfect complementarity between the guide and the target, which you have for on target. We're saying, well, did it accidentally do something there? So now we need to consider mismatches between the guide and the target. And moreover, we need to do that across the whole genome. So now suddenly, instead of just saying, does this guide and this target, is it going to cut and knock out the gene, I need to scan the entire genome, and then I need to somehow predict how active is it going to be at each of those places in the presence of some number of mismatches. So this is just like actually wildly more difficult and computationally expensive. And so, I mean, one is I have to scan the whole genome, so that by itself is really annoying. And then from a modeling perspective, the fact that I have to tolerate mismatches means, and I guess in computer science lingo, we say this is like a combinatorial explosion of possibilities. And I'll show you how it explodes. Is that the next slide? No. But so the more mismatches I tolerate, kind of the more examples I need for the model, because there's just so many possibilities. And there's actually, I think there's even less data here than for the on-target, depending how you count data, but it's really, really limited. Right, and so there's very simple 3 steps here. It took us a while even just to get to that. And so ultimately, though, this is how we think of the problem, is given a particular guide, our goal is going to be to find out where in the genome there are likely to be off-target activity using our model. And then we also want to summarize it into a single score for that guide. Because people don't want to, for a single guide, they don't want to ponder. I mean, they might for some use cases, they might want to do that, but I think a lot of people, depending again on the use case, they want just a single number with the option to drill down about where the off-target activity is. So what we're going to do is they're going to start with a single guide, and then we're going to scan along the genome and filter essentially to a short list of potential active off-target sites. And then once we have that short list, then we're going to use machine learning to score each of them with one of these predictive models. And then we're going to aggregate them all into a single score. And so most of the work that we did, all the machine learning is down here. And one could, in principle, actually use machine learning up here as well, but there are just already too many moving parts. And so we actually just stuck around to doing a heuristic, which is to basically cut it off roughly, actually, it's not at 3 mismatches. So I just realized this slide is something a little bit different. I think it actually goes up to 6, but it allowed to ignore the 3 distal or something like this. So I apologize, I don't have exactly the right details here. But this shows you what I was talking about, a combinatorial explosion, which is if I tolerate only one mismatch, so this is a back of the envelope calculation, right? Let's say there's 100 sites genome-wide roughly, and the more I go, the more sites I have to consider. And so when I do this filtering down to a short list, I can only go so far. And that's also why actually it stands to reason the machine learning could maybe do better here, because this is a very rough criterion of just number of mismatches, and we know that that's not what's driving the model because we've done the modeling. It definitely has a big impact, and so it's not a bad thing to do. Right, and there's lots of software out there that actually does this, tons of things that will go and find all of these things for you. And I guess our add-on contribution is really to do the machine learning on top of that in a way that is really better than what's out there. Right, so that's all I'm going to tell you about this first step. It's basically just a heuristic where we say we allow up to some number of mismatches. Now that's our short list for this guide. So right now the problem is how do we score the off-target activity for each member of that short list? And so there have been some previous approaches on this from your community that's putting out these great papers, and they're making very clever models that actually do surprisingly well in a lot of cases, given that they're sort of declared by fiat to be the model. It's really amazing. And so we thought let's bring in machine learning and see if we can do any better here. And at the time we started to do this, TFD, which actually was John's model, in the paper we wrote together, but we ourselves didn't get to the off-target problem because we were just didn't have time for that paper, is basically counting frequency of knockdown according to some very simple features. And I'll tell you a little bit, I think a little bit more about that. And so we're going to, again, do this machine learning thing. And so the last picture I showed you like this was for on target. And in that picture, it did not show you the target. If you might recall, it had only this one column, which was the guide, and then it mapped directly to the activity using just the guide. And so, but now, because of the mismatch, I have to include the target as well, right? And on target, by design, these were complementary, and so this was redundant information. But now, there might be mismatches between these, so if I know this, I don't necessarily know that, so I have to throw that into the mix. And so now, this function I want to learn is a function of the guide and the target, and then I'm going to play the same game. I'm going to get as much data as I can, and I'm going to try and learn this function. And actually, in this case, we're using only 23 mer, not 30. And the reason for that is I just think the data sets we had 23, and it was a real pain to make it 30, so we just left it at 23. So these are how you store your data in your Excel sheets may impact how we do machine learning if we get a bit lazy. Alright, and so now I need to also play this game again where I go from these, now the guide and the target, and go to some vector. And mostly I'm going to do the same thing I did for on target. So everything I already told you, I'm going to do that for the guide again, and that's going to go in here. But then I need to somehow also encode the mismatch. And I can do that in different ways. I could, for example, I could just say there is a mismatch at position 8, but not tell it what it is, and then separately say one of the mismatches is a T to an A. Or I could say there was a mismatch at position 8 and it was a T to A. And so there's some flexibility there, and we actually do several of those things. And again, if we had enough data, we wouldn't actually have to enumerate these different things. We would just kind of give it the components, and the model could figure out what the features should be, but we have very limited data. And then it gets, this is where it also gets super complicated. So again, I mentioned this sort of combinatorial explosion of possible number of mismatches. So like, I don't know how much data there is that has multiple mismatches, but it's like, you know, maybe 1,000 examples. And you saw how many mismatch examples there were, right? Like, I mean, thousands and thousands. So we have almost no data, I would say. Almost like no data. However, what John did is he built, and this is kind of going to sound insane, I think it is insane, but it actually works, is he took just CD33 and he enumerated every single mismatch guide target pair, and he measured the knockout efficiency for that. And from that we can, like if it's just one mismatch, we can build just a one mismatch model and not consider the combinatorial explosion. And that gets us a one mismatch model. And that's actually what we do, is we build this one mismatch model just from CD33 data, and I'm super curious to know if we actually had some more genes in there, how the performance would change, since in general we're not at all testing on CD33 here. And then the thing is that we want to be able to take any arbitrary example and kind of bootstrap ourselves using that single mismatch model to get a prediction for it. So how am I going to do this? What I'm going to do in the first, on this slide so far, is I'm going to pretend that this 2 mismatch, or it could be 3, if there was 3 mismatches, there'd be another figure here. I'm going to break it down into examples, like pseudo-examples of single mismatch guide target pairs, even though that's not what it was. And I'm just going to do this because I don't really have a choice, because there's just not enough data. And then I'm going to assume that they are, for example, independent. And if they're independent events, I can multiply them together and I can get a score. But it's not really independent, and it's not really the right model, so we're actually going to use a very limited amount of multi-mismatch data with a really simple model that has very few parameters to actually learn to do something better than multiplying them together. And that buys us a little bit extra. It doesn't buy us a lot because there's just very little data, so there's not a lot we can learn. And if we had more data, we could probably do much, much better here. Does that make sense? How I take CD33 single mismatch data, I build just a single mismatch model, which we hope is not specific to CD33, and it's clearly not, because we do get some optimization performance, but to be clear, off-target prediction is actually not great. It could be, it's pretty low. And then we break down examples into the single mismatch, and we could, in principle, just multiply them together, and that would actually not do that badly, but we add on a layer of machine learning with a very limited amount of multi-mismatch data, which we get mostly from guide-seq data. And we're doing all unbiased assays here for off-target, because we don't want to focus on kind of weird things. So we're doing unbiased assays like guide-seq that search over the whole genome, even if they're not as sensitive. And again, right, so we actually use these boosted regression trees for the single mismatch model. And then this is, I said we have to use a very, very simple model here because we have so few examples. And here we just use linear regression. And actually, you may not know what L1 penalized is, but it's basically a super constrained version of linear regression where you kind of force or coerce the parameters to be closer to 0 than they would otherwise. Yeah?
For the previous slide, in the second consideration of selected affinity mismatches, for example, here you have a
yeah.
Where's the GT?
Right. So it doesn't do it in the sense that we don't compute binding affinities of those things, but we give the model that information that it was a T to a G. And so if it has enough examples of that to tease apart that was useful, then it could, in principle, learn that kind of a thing. Yeah.
This doesn't take into account the nearest neighbors.
So, actually, yeah, in this layer here where I said we do something that, so we could multiply these together, but instead we learn a model here. In that model, some of the other models out there that were not machine learning take into account how close together the mismatches were and things like this. I think that's what you're maybe asking, or,
actually,
no.
So, if a TC mismatch is in a TTT context on each side, it'll have a different stability than if it's nasal.
Right. So we implicitly have the ability to capture that, and the way we have the ability is that when we encode this mismatch, one of the ways in which we encode it is we say there's a T to C mismatch in position, I don't know what that is, 7, and then separately we have features that say there's a T to C